Okay, so now I'm going to review a number of results that falls down to ask this question. We're going to expand to use polynomial expansion for this solution map in the case of the model problem that I gave, but for other problems too, and ask whether you have some ability for these guys, in the sense that you can put this to a small power p and sum, and this is finite. Okay? So here we are going to take off a little bit. I mean, it's going to be more difficult. This is the most painful hour, unless you are interested really in this. But I hope I give you a flavor, and then we will land tomorrow. It will be much, I guess, easier and more general. So don't get nervous if what I tell this hour seems difficult, okay? Because we will sort of slow down tomorrow. I think it's good to do this way, not to end by the worst and to sort of land smoothly, okay? So I'm going to investigate first this guiding example. You remember, A is parameterized this way. And you have this uniform assumption. Okay, right from the start, because I'm really interested in understanding if I can get a rate which is sort of immune to the dimension of the vector y, I will immediately assume that this is an infinite series. Okay, so I'm being quite general. And of course, this subsumes the finite dimensional case, because you could say that some of these psi j they are all zero after a certain while. That would drive you to the finite dimensional case. Okay, but I will really work in this general case. So now this box y is an infinite dimensional box. There's countably many variables, and this lattice has countably many dimensions. That makes the problem of picking the right points even more critical. So we have this uniform ellipticity assumption. Let me give two different expressions of this assumption, which are actually equivalent. Because you see, you want that this holds whatever yj is between -1 and 1. Okay? So you can take, for every x, you can take the worst case value, the one that makes it the smallest. So you take the sign, or minus the sign of psi j of x. And in order that this is bigger than r, you see that you get this condition. Okay? And the sum of the moduli of this guy, or the absolute value, is bounded by, is a little bit smaller than a bar of x minus r for all x in D. Okay? So the total sum is dominated by the nominal term. That's what uniform ellipticity means. Or another way is to write it this way. Okay? To say that you bound this way. All these are more or less equivalent. And you have uniqueness. You have a uniqueness of the solution existence and a uniform bound, as I wrote below. Okay? So we're going to do the simplest, for the moment, the simplest polynomial expansion, something that you are usually in numerical analysis, it's not recommended to do that, right? To do power series. In that case, usually you prefer orthonormal polynomials like Legendre or other things. But in that case, this will be effective, that particular case. Okay, so I'm expanding formally for the moment. We have to prove convergence of bits. And so what are these T nu, the Taylor coefficients? They are just the partial derivative at 0 normalized by the multifactorial. Okay, we are in several dimensions, so this new factorial stands for the product of the new j factorial, and you have this convention. Okay, that's just multivariate Taylor power development. Okay, and f again is all the set. You're only looking at total finite total order of differentiation, of course, or I don't know what it would mean. And so F is a set of all finitely supported sequence of integer, and you have this lattice. And yeah, our goal is to identify this set, a good set lambda. And according to what I told you, you see, if my Taylor coefficients have this amount of LP summability, they are in LP for some p strictly less than 1, then I can apply Stechkin lemma. And I get that this tail, if I take the largest for lambda and the n largest of this guy, this tail is like n to the minus s. Decay is like n to the minus s, and s is 1 over p minus 1. Because here it's the L1 norm, so it corresponds to q equal 1 in the general results. Okay? So that's very clear. And so the question now becomes, under which circumstance do we have that these Taylor coefficients, once we measure their norm, are LP summable for p less than 1. And here is a result that is quite simple in its formulation. So what does this result say? It's a result we are quite happy with when we obtained it. It says that if you have this uniform elasticity assumption, then the following holds. So remember, these psi j are the basis that you use to expand the diffusion field and to reveal this variable y1, yj, okay? And what it says is if this psi j, when measured in L infinity, are LP summable, so if they have some kind of decay, then these T nu are LP summable for the same value of P. That's the result. Very simple. Okay? Now let's look at this result before explaining how you prove that and see what it means. So, what is the good news with this result? The good news is that you're going to receive a rate of decay which is polynomial, despite the fact that you are in infinite dimension. So it looks like you broke the curse of dimensionality. Okay? According to what I said, but there is no free lunch here. Huh? What is happening, in fact? What's happening is that you have this condition on the decay of the psi j, and that's an anisotropic condition, because you can imagine that when j becomes large, this psi j becomes small. That means that the variable yj will have less and less effect on the phenomenon. Okay? In a way, psi j describes the sensibility of the variable yj, because it's attached to this variable yj. Okay? So this is what makes it possible. And it makes it possible because you also pick the right choice of coefficient. If you were taking some classical polynomial space like tensor product space or total degree or sparse grid or this kind of thing, it would not work. So you really need to pick this set in a good way. Okay? Okay, let me say that I'm giving this result for this model problem, but it immediately carries over to more general linear elliptic equations of this form, so where the operator depends in an affine manner on the yj. So you could think of a whole class of equations. What I will explain carries over to these models. Also carries over nicely to parabolic equation, but not so nicely to hyperbolic equation. There is a significant difficulty to move this theory to hyperbolic. And so I'm going to explain how you prove this theorem. I'll give a little bit of intuition. And the proof, the first proof we have, I'm going to give actually two different proofs, two ideas of different proof because it would take too long to give the detail. The first idea is to use complex variables, so it's quite interesting. It's to move to the complex variable and to use an idea of holomorphy. I think Ron evoked this idea of holomorphy. So remember, we want, in the end, what we want to do is to prove something on the summability of this T nu. So in order to prove summability of this T nu, we need some estimate on this T nu. Right? We want to estimate them. We're going to estimate them by complex analysis arguments. Okay? That means that we are going to try to extend, to do a sort of holomorphic extension by replacing this y by a vector with component in the complex plane. Okay? So remember, we have this condition for uniform ellipticity, and this condition for uniform ellipticity tells you that when you look at A of z, when you replace this y by complex number, as long as this z have their moduli now less than 1, this A of xz has its real part bigger than r. Okay? And now you have to make the observation that it's not too difficult, but you can check that this is enough. This also works to apply Lax-Milgram. So it means that you will be able to define the solution also for complex valued guy as long as you have this condition. So the set Y, this box, is now replaced by this polydisk. Okay, this tensor product of a complex unit disk. Lax-Milgram theory applies. It's a nice observation. And the second thing is that this function is very nice as a function of z. Sorry, it's not u. It's z maps to u of z. This is a typo. This is a function that is holomorphic in each variable. You can differentiate it. So how do you differentiate, by the way? I mean, we should all know how to differentiate this thing. How does it work? We look at the variational formulation. We write it this way: integral of a of z grad u of z grad v equal integral of fv, right? That's the variational form. And now we differentiate everything with respect to, let's say, z1 now, zj. Okay, what happens if we differentiate? Well, here, if we differentiate, this does not depend on z. That gives you 0. And here there is two things that depends on z. There is a of z and u of z. Okay, so you just apply Leibniz formula, and you see that you have two terms that come. You have this one, and you have this one. Psi j is what comes when you differentiate a of z with respect to zj. Right? When you differentiate this with respect to zj, you get psi j. Okay, so you see that you get a derivative, a complex derivative that is given to you as a solution to a boundary value problem, actually. It's again a solution. You can look at this at any point z. Okay, so we know that holomorphic functions have all kind of nice property. And what's going to be important is not the fact that it's holomorphic, but where it's holomorphic. What are the domain of holomorphy? Okay. So now I'm going to make this remark that not only I am holomorphic in this polydisk, but I can move a little bit further. If I take any sequence of weights such that this sum is less than a bar of x minus delta, that means that when z is in the polydisk with radius omega j in each variable, what I call u omega, then I have ellipticity, except that this little r has been replaced by this little delta. I could take delta smaller than r. And so that means that I'm going to have holomorphy with a uniform bound, but in a possibly larger polydisk. I'm going to be able to extend. Okay, so I can move away from this unit polydisk and say I have something. All right. So why does it impact the Taylor coefficient? It impacts the Taylor coefficient because you can apply Cauchy formula. So Cauchy formula, let me recall what Cauchy formula says in full generality. It says that if you have just in one complex variable, what does it say? If you have a function which is holomorphic in some open set U, O, that's an open set of C, and you are holomorphic, you take any closed curve gamma in the interior inside O, okay? And then Cauchy formula tells you that if you want to evaluate U at a point, at an interior point, U of Z, this will be equal to 1 over 2 pi I times the integral over gamma of U of Z prime and divided by what I just wrote, Z minus Z prime, dZ prime. So it's a contour integral. So Z lives here and Z prime goes along here. So if you follow the basic course on complex analysis, this is maybe one of the first thing you learn. And that is a way to give you estimate on the derivative, because what's going to happen, you differentiate n times at z equals 0. So in that case, think of a disk. Think that gamma is just a circle of radius b. You differentiate, and then you have powers that come here when you differentiate with respect to z. So this power, because you integrate at distance b from the origin, if z is equal to 0, you get these powers here. And you also get factorials. The 2 pi disappear with the integral if you know that you are bounded on this polydisk. So if you are bounded, if you have a bound on this disk, you receive a bound on the Taylor coefficient once you divide by a factorial n, which decays exponentially and decays faster and faster if the radius is large. Okay? So now we have a function of many variables. But this is essentially the same story. We have this polydisk, omega j, in each variable. So we're just going to apply recursively this formula. And because we differentiate mu j time in the variable omega, in the variable zj, well, we get this estimate, which is just a generalization of this estimate. And this is the bound that we have, that I gave before. Okay? The bound inside this polydisk. And so the coefficients are given by this. They are given by the product of these omega j to the minus nu. And this is, again, true, provided that you have this bound, this control that tells you that you are in the ellipticity region. So this is an estimate. What can I do with this estimate? Well, what do we have? So the Taylor formula, the Cauchy formula tells us that you have a bound on Taylor coefficients. So, of course, we would like that this omega j are quite large. It would be good, because the larger this is, the smaller this is. But we have a constraint here. Okay? So now we can play. We can try to say, how can we infimize this given this constraint? Okay, this is a constraint that is due to the need to have ellipticity. Okay? And if you look at this problem, it's not such an easy problem to solve. Actually, in full generality, I do not have an explicit solution to this problem. Okay? So we don't have a solution. I'm going to give an example where I can explicitly give the solution, but this is a very particular case. This is when the psi j have disjoint support. Okay, so this is where the real difficult part starts. We have to build a good choice of omega that satisfies the constraint for every nu that satisfies this constraint. And we take a delta which is slightly smaller than r over 2. And then once we have this choice, we have to really take care on how we build it. I'm not going to give this detail. We can prove that this condition implies that this bound is LP summable. Okay, you can make this work. So that's a way to prove the theorem, but I'm hiding a lot of difficult detail on how you now construct this, because you cannot solve exactly this optimization problem. Let me give a simple case where you can understand what's going on. The psi j has disjoint support. So that means you maximize separately, because you see your interest is to have these omega j's the largest as possible. And now these constraints are decoupled because they don't play against another. They have disjoint support. The supports are disjoint. So what are you trying to do? To take this omega j the largest as possible. So to have this, and this is going to be given by this formula. Essentially, you'll have to take omega j inverse proportional to psi j. If psi j is very small, you will be allowed to take omega j quite large. Okay, so that is the sensitivity. You see that if psi j is very small, your variable is not too sensitive, and you can take a very large radius of holomorphy. So in that case, this omega j is clearly given. This is our estimate. Let me, for convenience, I'm introducing the inverse sequence. Bj is just omega j minus 1. So Bj is essentially something which is it's going to be smaller than 1. And it's going to be also bounded by the L infinity norm of psi j. Okay? So you see you have a very simple thing now. You have this bound now. The bound is very simple because T nu is bounded by this constant C delta B to the nu. And you want to understand if you have summability. And now the result, the observation is very simple. The observation, so our assumption in the theorem is that this psi j, L infinity are LP summable. And I claim that if you have a sequence like that, if it's LP summable and every member of the sequence is strictly less than 1, then this is equivalent to having that this power are LP summable. And that's quite simple. In that case, it's written at the bottom. I think I don't need to write it. You look at the sum of this b to the p nu, and what is it? The sum, and here you see that you have bj to the v1 to the nu 1, b2 to the nu 2, bj to the nu j, for all possible choice of nu 1, nu 2, nu j. So you can factorize. This actually factorize into the product in j of this sum. And this sum, because bj is less than 1, is given by this. So you get a product, and this product converges because the sequence is in LP. Okay, so that's, in that case, I think this is a nice little result. It's a nice observation. If you have a sequence B which is in L infinity less than 1, it belongs to LP. So it's just B is just a sequence Bj of positive number. Then this implies, but it's actually equivalent to say that the sequence B nu is also in LP of F. Now the B nu is all these B nu being the product of Bj to the nu j. Okay, so that's, so you have to play with this kind of this game where you start from a sequence just indexed by integer, and you land to a sequence which is indexed by infinitely many integer, but actually very nicely you retrieve the same kind of result. By the way, it's very interesting for those who know a little bit about interpolation theory. This is a funny thing. We're asked, do you have similar result if you replace LP by weak LP? Would you have that if B is in weak LP, this would give you weak LP, right? That's for the specialist in this area. And the answer turns out to be no, which is surprising because you would say that by interpolation argument, if this is true for all P, that should also be true for weak LP. But the problem is that this thing is a completely nonlinear mapping. You cannot apply usual argument. Okay. I just want to say that we can improve on this result by. So that was the situation until 2015. We thought really you have to go through complex analysis, and then we came out with a completely different idea, which in some case sort of works better than the complex variable argument. But I'm not sure I will have the time to develop this. So it's an improved result where, but which is very, very specific to the particular model of the diffusion PDE. So one of the limitations in this previous result is that the dependence on the psi j is only through their norm. So for example, it doesn't care if these psi j are very localized. Imagine that you have something that happens in a very small period of space. You would like to say then it's yj will be less sensitive in a way because it doesn't impact much, but you don't see it because you just measure the PL infinity norm. So we wanted to have something a little bit sharper, and we came out with a method using the real variable now. Okay, and the idea for using the real variable was really to look at what I raised, the derivation of the first order differentiation by differentiating, but recurse, continue this. So if you look at what I wrote on the board, when you differentiate with respect to the parameter, you can continue. And what you find is that the Taylor coefficient for a certain nu are solution to a boundary value problem, where on the other side you have the Taylor solution, the Taylor coefficient for lower differentiation. So nu minus ej means simply, ej is a Kronecker vector, so it simply means that you differentiate 1 times less in the variable j. Okay? And bear with me that this formula, you can derive it just by recursing on the very first from the very first formula. So you can use that and play a little bit with this. You see, when you want to estimate the Taylor coefficient from there, one typical thing you would like to do is to take V to be T nu itself and play some game here with Cauchy-Schwarz or Young inequality and get some estimate on the T nu from the previous ones. So you play this game, and I don't have time to explain the game in much detail. But what does the game tell you? I mean, here T nu is really, the norm is really essentially given to you by that. This is the quantity of interest. And you play with some recursion, and the final thing you can prove based on that is that whenever the uniform ellipticity assumption holds, these guys are going to be not only bounded, but summable. So you can prove some kind of decay, which will help you prove that the total sum of the d nu is finite. So it means that these t nu square are finite. And what you next do is introduce weights. So now, before we had that if the sum of the psi j divided by a bar was less than 1, we got that this Taylor coefficient were square summable. Now we put weights, and we are assuming this improved uniform ellipticity assumption. And you see that when you put weights, that essentially means that you are going to consider the solution evaluated at a rescaled value of y. Okay? Because this thing is just the solution when you replace psi j by this omega j psi j. Okay, so for this rescaled guy, you know that the Taylor coefficients are square summable. This is what I wrote before. Well, I went pretty fast actually, but what you prove by recursion. And now because you rescale, these t nu are just given by omega to the power nu t nu. Okay, that's just because you have rescaled. And so you get a weighted L2 estimate. So it's not an LP estimate, it's a weighted L2 estimate. But it's actually a little better than one we got for complex analysis, because if the sum is bounded individually, this T nu is bounded by omega to the minus u whenever you have this relation. So this is very similar to what I had before, but it's a little bit better, because from an L2 weighted L2 estimate, you can get to an LP estimate by using a cleverly Holder inequality. And now you have something very similar, because here you have a sum which looks which I can treat by the same kind of result that I gave before. Okay, so here you have P, you have this thing, and you have a Q which is related to P by this relation. That's just Holder inequality. And this, the sum in the second factor is going to be finite, provided that omega j to the minus 1 is in LQ. So what is the final outcome of this? It's a bit different from the theorem from 2011. It says that if P and Q are related by this relation, if you have this condition on the psi j with the omega j that grow fast enough so that their inverse is LQ summable, then these T nu are in LP. So it's look a little bit less simple than the previous theorem, but it's actually more effective, because this condition is pointwise. It's not a condition on the norm. It's a condition on the pointwise value. And so it will be much more favorable if these psi j do not overlap. You can exploit that. OK, so that's a completely different way of proving these things. And for example, in the case of disjoint support, you gain, actually. You use this, and you prove that actually if these psi j are in LP, then the T nu are in LQ, sorry, then the T nu are in LP. So it's actually better than what I had in the previous theorem, because Q is actually larger than P. Okay, so for example, if you want P equal 1, it suffices to have Q equal 2 here. All right, so this is just a variation, but all right. So now I want to briefly talk about other models and end by something we did recently. So you could have all kind of other models. You could have very similar PDEs, but no affine dependence. So imagine something like this, for example. I'm just putting a dependence where I put a square. This is just a toy model. Okay? So then ellipticity is sort of guaranteed just because this thing is positive, you don't have problems. You could introduce nonlinearities. Okay, think of something like that, where you could put, for example, a nice monotone nonlinearities, so that everything is fine again. Or you could consider a fixed PDE, but where the parameter enters the domain. So here I'm just taking the Laplace equation, but you could think of all kind of fluid equations. And I'm considering a domain where the parameter describes the boundary. So to be very simple, I'm taking a little box. You see, my domain is a box, this model. That's my domain, D. And the top of the box is a function. Okay? Just to have something simple, but the whole domain. So you can think of this Yj now as control point. And you see that I take these functions to be depending on this Yj like that. So this condition is now just a condition that you don't want self-intersection of this domain. You don't want that this goes down to the boundary at the bottom. Okay? So you could, the one way to have a good treatment of this problem is typically to transport it back to a reference domain by a good transformation. And now you have a different PDE on the reference domain. Okay, by a good, so you map it back, domain dy to the box, but now every time you have a different y, you get a different PDE, of course. All right, so you look at all these models, and the bad news, compared to our model 0, the first guiding example, is that what I told you will not work. It will not work as nicely. You will not be able to do Taylor expansions, because Taylor expansion means essentially that you can replace this interval, this box, by a complex disk of the same radius. It means you are able to make a very long extension, a good excursion in the complex domain, and remain well defined. So I claim that in all these models, you have trouble when going to complex domain. Try a little bit to think about it. For example, here, as soon as you put an I, this square is going to become negative, and you're going to have trouble with ellipticity. Okay, so you're going to have all kind of difficulties, and for different reasons, here and here, you will have difficulties to do holomorphic extension, or at least as far as you want. That's the bad news, but the good news is that if you replace Taylor coefficients by Legendre expansion, so you take the Legendre polynomial, you tensorize, which is a much more sensitive thing to do. You take orthogonal polynomial, then things are going to be much better. So in that case, what it is an orthonormal basis. So you take these L nu, these are the tensorized Legendre polynomials. Your coefficients are just given by these integrals. Okay, you could also normalize these Legendre polynomials in L infinity. And the result in that case is that for all these models, you get a similar result as the one we had initially for the first model. Okay, so summability of this guy gives you summability of this guy, but these are now the Legendre coefficients. And so immediately you see that you retrieve by Stechkin argument, you're going to retrieve convergence rate in L infinity, but also in L2 because of the orthonormality of the Legendre functions. So instead now the rate will be 1 over p minus 1 over 2 instead of 1 over p minus 1, again because of this Stechkin lemma. So, right, you can also improve the summability result for Legendre expansion similar to Taylor expansion. So I do not have the time to explain why this works, but just give you an idea what's the difference between Legendre and Taylor. So remember how you compute the Taylor coefficient, how you estimate them for an holomorphic function. It's really related to how large you can take a disk and remain bounded and holomorphic, and then you have this exponential decay. Okay? So what happens with Legendre coefficient, and more generally, same thing for coefficient with using Jacobi polynomials, so you could use Chebyshev polynomials, other things, you have similar estimate, very similar. You see there is a little algebraic factor which is harmless. But what's going on is that you are allowed to retrieve this estimate with a much shorter excursion away from the real valued domain than in the case of Taylor. Namely, what you need is to be bounded and holomorphic in an ellipsis where the large axis is essentially like b, it's b plus b minus 1 over 2, so when b is large, it's going to be like b. And the small axis is going to be b minus 1 over 2, so when b gets close to 1, this is much more concentrated near the interval than this disk. And this is really what allows you to make all these things work. You are not obliged to go so far in the complex domain. You just need a little perturbation, and that is something you're going to get essentially for free in this model using the implicit function theorem that will allow you to move a little bit away, but not too far from the real valued domain. So this is just to give you some intuition why orthonormal expansion like Legendre are more friendly than Taylor expansion. Now let me finish by one last model, which is the log normal parametrization, and which is a little bit more nasty in a sense. So in that case, I'm again looking at the diffusion equation, but now my coefficient is going to be the exponential of a Gaussian random field. So a Gaussian random field which will be described this way. So I'm again assuming that I have a sequence of functions, and these yj now are independent standard Gaussian variables. So when you do that, you have a Gaussian random field, and I'm assuming that A is the exponential of this field. Okay? So what does it mean? It means that now these y, they do not range in minus 1, 1. They range, these yj range in the whole of R. So y range in Rn, but equipped with a probabilistic structure associated with the Gaussian distribution. Okay? This is a model that has been considered often in porous media. Why? Because people want to describe with this model the fact that the diffusivity could change drastically. You see, a Gaussian process can sometimes be very small, very large negatively or positively. In that case, this could become very large or very close to zero. You don't have uniform ellipticity, but you can control still the degeneracy, the fact that this goes to zero, because you have the Gaussian distribution. So the probability that this gets very large is going to be controlled by the Gaussian distribution. That's the idea of this model. Okay? So what do we have actually? Again, by Lax-Milgram estimate, you can bound this. You know that U will be well defined. Whenever B of y is in L infinity, because in that case this thing will be well defined and elliptic. And you're going to have this estimate. Okay, so you have the exponential of B of y in L infinity. Okay? So that's just what Lax-Milgram gives you, a crude application. All right, so what are the main questions? Okay. One first question is integrability. Because, of course, this thing is not uniformly bounded anymore. With a little probability, this B of y could be quite large. But this happened with small probability. So the question would be under which condition this map is maybe not uniformly bounded. This is no hope, but at least integrable. For example, you could ask, do you have moments for all values of k? Do you have this? Okay? And in view of this estimate, this means that you would like to understand if this expectation is finite when you elevate this to the power k. Okay? That's integrability. The other question, which is more interesting to us, is approximability. So suppose that you've already proved integrability, that you are in L2, then you can use an orthonormal basis. And the natural orthonormal basis now is the Hermite expansion, because you have the Gaussian measure. So you're going to take the Hermite polynomials, which I recall are orthonormal with respect to the Gaussian measure. You are going to tensorize them, just like you did for the Legendre coefficient, compute these guys. And of course, now you may ask the same question, under which circumstance can you say that these coefficients are LP summable in order to retrieve some approximation result? Okay? So two types of question. That's the result we had for integrability. So the integrability is essentially not such a difficult problem. I mean, you're going to have all moments, of course not for k equal infinity, for reasonable, with reasonable assumption. As soon as, for example, the covariance function of the field has some little Holder smoothness, or if you just have a little bit of just this summability for the psi j, I mean, you have all kind of possible condition. Approximability was a little bit more difficult. So when we came to this problem, the result that had been proved was the following. So if you look at this result, it's a little bit less, more pessimistic. If you remember what we had for the Taylor coefficient and the affine parametrization, the first model problem, you didn't have this j here. You just had that this implies this. Now you have this j, which makes this condition much more tough. And so with a little bit more work, what we proved is something very similar to this improved summability result, which is essentially the same. As soon as you can put weights on this psi j that grow such that their inverse is LQ summable, then you have this. Then you have LP summability. Okay. So I'm not going to give the proof. This is sort of useless in such small time, but this uses ideas on Hermite polynomials. And the difficulty is really to look at this, to differentiate the equation. You see, I gave a formula in the case of the affine model to differentiate. In the case of the log normal model, it's the recursion formula is much more nasty because it involves essentially all the terms. And this is why this is more difficult. So I'm really not going to give the detail, but those who are interested I can explain if they want in private. Okay. So that's a conclusion for today. What I wanted to show is that the curse of dimensionality can be defeated by exploiting smoothness and anisotropy in the different variables. Anisotropy is the key. Anisotropy is expressed through this psi j, which has certain summability property. And for these models, everything can be done by sparse polynomial approximation. This is sort of nice. Yeah, that's interesting. The way we parameterize the problem or the way we represent the solution is crucial. I didn't really say that, but when, for example, when we have a Gaussian random field, we may have different choices for this psi j. Imagine a Brownian motion for B. You could represent it with the Karunan-Love basis, which is like Fourier basis, or you could represent it with wavelet for this psi j. You would not have necessarily the same result. I do not entering this. And so far, you see what I did are approximation result. I gave you the result that for several models, this solution map can be well approximated by some multivariate polynomials. Okay? And these multivariate polynomials are computed by taking certain series and keeping the largest term. But this is really to prove a theorem. This is certainly not a numerical method. Okay? For many reasons. Huh? What are the obstructions? What is the difficulty? The first is that for sure you will not be able to find this lambda n exactly, right? Because you would need to explore the whole universe of coefficients and identify which are the largest one. That's a problem, okay? So you need to do something else. I mean, so what you need to do is to identify something which may not be the optimal choice, but at least good and give you the same thing. And secondly, all these polynomial coefficients cannot be computed exactly, right? You cannot compute that exactly. You need to do something else. And this is where least square will come into the game as a vehicle to provide something which is computable. Okay, so I'm going to develop this tomorrow. So let's stop here, I guess.
Any immediate questions? In the log normal case, Javier, do you compute? You have explicit bounds on the moments for UK, or do you just need them to be finite? If you had explicit bounds, then there are concentration in these.
Yeah, but so it's interesting. Okay, this is not the vehicle. So you can compute bounds for these moments. I mean, these moments indeed. I mean.
Then you could have concentration inequality.
Yeah, you can compute that. But this is not this bound. It's not because you are in LP with LK with K bigger than 2 that this is going to give you extra summability of the Hermite coefficient. this is really two different stories. Okay, so it's really two different questions. If you look at some point in the estimate for the Hermite coefficient, we use, I think, at some point we need the fourth order moments to do something, to do computation, but there's really something else. The derivatives are important. It's not just integrability, you need smoothness. Okay? You need smoothness with respect to y. This is why in the proof we differentiate at some point. Yeah. You see we have some differentiation. That's sort of critical.
I see. So in the end you get by with Galerkin. You sort of absorb the degeneration by having it only happening with low probability.
Yeah.
Right? So that you get a mean square in expectation.
Yeah. So, okay, when you say Galerkin, you mean Galerkin with respect to the parameter?
I mean a symmetric variational problem, where the test and the trial spaces are the same.
Yeah.
Would it help if you put sort of the possibly degenerating weights just in the test space, which changes the test norm?
Okay.
And would you then get
so you refer to stochastic Galerkin.
Yeah,
so stochastic Galerkin is a problem with Gaussian with this model. Okay.
Yeah.
There is a real difficulty
Yes.
because you have a trouble in applying Sea's lemma because of the degeneration. So again, there's all kind of trick here, but now I will divorce from there. Okay, I will not consider stochastic Galerkin tomorrow. I think it's quite. The reason I like non-intrusive method is because they apply to a very large number of problems, but also for this problem, they will be quite nice because, as I will show you, there is a way to sample which is perfect for the Gaussian when you have the Gaussian distribution.
You will, with low probability, also sample at the bad places, so your solver will have problems there.
That's okay. That's true. So you will have to effectively account for that. There is always a price. I agree. Although you will see it's kind of interesting. You will see the measure that comes out. Because I'm not going to sample according to the Gaussian measure. I'm now saying a little bit what I'm going to do tomorrow. But I'm going to sample with respect to a different measure. Okay? So, yeah.
Good. So, there are no further questions?
Oh, he has a question.
So among the amount of problems, is it difficult to tackle the time-dependent problems as well?
No, okay. So in this big ACTA paper, but in fact in Chris Schwab, and I think he did that with Stevenson. So he has a sort of for certain parabolic problem, he has a space-time formulation that is okay. This is not a numerical method again. It's just to show. This is an instrumental to show that you have the right type of holomorphy. So it's no more an elliptic problem, but you recast it in a problem which is well posed in terms of an in-soup condition. Okay, so you have a pair of computable space, and you have an in-soup condition, and the in-soup condition is essentially what you need to make all these holomorphy business work. So everything works, for example, for the heat equation. It doesn't work good for the wave or the transport equations. For if the coefficients are in the velocity, you're gonna have a lot of things that break down. And probably these methods are not the good ones.
Okay. Good. Then, thanks everybody. We have a break now.